Hi everyone, it's me, Carolyn, and this video is going to go through the Poisson probability distribution. Again, this is a discrete probability distribution, which means it is going to give us discrete outcomes, not values on a continuous scale. That is still coming. But I'm going to walk through one example. I'll show you how to do it by using a calculator, and then also how to use software to help us out at the end. So first of all, we have a Poisson. What it does is it counts the number of occurrences, or we'll call those successes, of a particular event within a specified interval. A lot of times that interval is time or space. So like examples, counting how many people go through a checkout line, how many animals or critters live in a square mile, how many cars are there driving across a certain bridge. So those are some of the things that I'm talking about here. So Poisson probability does happen a lot, and this is sometimes how they determine how often they need to repair bridges, etc., and things of that nature. So the next thing I do is I did write down the definition for us. A random variable x, which we'll kind of use our favorite letter, is the number of successes follows a fixed Poisson process if, sorry about that. First of all, the probability of two or more successes is in any sufficiently small subinterval is 0. So if we're talking about people coming in a checkout line, we're not going to have them coming in so quickly that we can't count them. So maybe, even if we have them one every second, we still could get it down to like 0.03 of a second, still that 0. So we can find some small subinterval that's probability of having two people in that small interval is 0. The probability of success is the same for any two intervals of equal length. So what we mean by that is if I'm looking at my people in a checkout line, we might be looking from 10 to 10:30 and also from 9 to 9:30. So we'd have those successes, those time periods would be the same. Not always the case in this situation I just said, but maybe Tuesday mornings from 10 to 10:30 is pretty much the same every Tuesday morning. And the third kind of criteria that we need is the number of successes in any interval is independent from the other successes. So as long as they don't overlap, we allow for that independence. So like Tuesday of this week is going to be independent from the people that come in our checkout line 3 weeks from now. Okay, if we have those situations, we have the number of successes for a fixed length of time or spatial or whatever this length of fixed length, we're going to call that t. The probability of having x successes in that interval is given by, so x is equal to x. We have this funny looking Greek letter, kind of looks like a backward H. It's called lambda. And then we have t. This whole piece is raised to the x power. We have e, which is just a number like pi, except it's about 2.713 I'm wrong, 2.718. And then we have it raised to the negative lambda t all over x factorial. And now notice x is the number of successes in a certain interval. So x could take on values. We would have 0 all the way on up till who knows when. Discrete does not necessarily mean finite. So we could have any number of successes that we are talking about. Okay, again, lambda, this little Greek letter here is our lowercase lambda. Looks kind of like a backward H in a way. And it is the average number of occurrences in some interval of length 1. So the example that I'll be doing, we will have to actually find lambda. All right, so here's the example that I'm going to walk through. And we're going to use my garden. I didn't actually do this, but my garden is approximately 500 square feet. That might be a little big, might be a little small, but we're just going to say it's 500 square feet. And let's just say, for argument's sake, that I did sample a few 2 square foot sections. So, 2 foot by 1 foot sections. And I counted how many weeds there were. And what I found is that I had about 5 weeds in every 2 foot section. I guess that would be pretty good. It's not too bad. Okay. And what I want to do is find what is the probability of finding 25 weeds in a 10 square foot section. Okay. So we're going to kind of walk through our example, our formula, and then we're going to actually find the mean of this situation, the formula for that, and then we'll go to finish up this video with our use of technology to help us out. And we'll just kind of verify that we did it correctly on the calculator. So, all right, so here's our situation. X is equal to, in this case, we're looking for 25 weeds. Even though we consider that a success, in my book, finding weeds is a failure, but we'll go, that's just terminology. And I'm going to have to do our wonderful formula. So our formula, again, looks like, have this lambda t raised to the x power. We have x factorial here on the bottom, and we have e to the negative lambda t. Okay, so I'm going to kind of walk through the pieces. In our problem here, the little x, that's the 25 that we're concerned about. Again, in these problems, we could talk about more than, less than, less than or equal to, all those situations. Again, I'm only going to show you one example today, very similar to what we did with the binomial. So the technology is very similar to that, where we can just change our inequality symbol in StatCrunch. So, but our x is going to be 25. Our lambda, remember, is the average of occurrences that we find in an interval of unit 1. So we found 5 weeds every 2 feet, which means our lambda is really 2.5. I'm just dividing that 5 by 2 weeds per foot. So my unit is going to be a square foot. And I should put squared foot here. Square foot. So a foot by a foot. So an area of land. You can do areas in terms of a linear area, like crossing a bridge. We're counting how many people go across that bridge. Just kind of, that's the area that we're talking about. We can also then need to find our t. T is our 10 square feet that we're looking at. Okay, so now I'm just going to put all our pieces in. So we have our lambda, which is 2.5. I'm going to multiply that guy by 10. That's our t. We're going to raise that to the 25th power. We have a 25 factorial on the bottom. We have e to the negative, and again, lambda times our 10. I'm going to clean that up just a little bit and actually multiply this 2.5 times the 10 so I can write it a little easier. So that's 25 to the 25th, e to the negative 25, all over 25 factorial. Okay, the fact that we had 2.5 times 10 to give us a 25, that's just a coincidence. It just turns out this time that we have lots of 25s floating around in there. So if I changed this problem and had 3 weeds, this would have been a 1.5, this would have then been 15. And that would have been a 15 as well. Okay, but I'm going to go to my calculator so that we can actually get this value. Okay, get rid of my stuff here. So I'm going to take 25 and raise it to the 25th power. And this is going to be kind of big. So just kind of let the calculator do the work. So I'll give it a minute. Okay, I don't know if you can see that. There's a glare. Sorry about that. And then we're going to multiply that by e to the negative 25th power. Now my e button is kind of right here above the natural log. It's at e to the x. So I'm going to hit that. I'm going to do times, get my e, and then I need to write it as the negative 25th. For me to do that, I have to hit the negative button and then 25. Okay, I'm going to get those. So now what I've done is I've multiplied these two together, and I need to divide that by 25 factorial. So again, divided by 25, and the factorial button is in our PBR. I'm going to arrow over to that, get that guy. You'll see it's dividing by 25 factorial, and I come up with 0.079522951. Okay, and we will double check that with some technology as well. So practice, make sure you can get that with your calculators also. Okay. I do want to find the average. What is the average number of weeds in this 10 square foot garden? Okay, I want you to remember that when we're talking about discrete random variables and we're talking about the average, it's also thinking of it as how many weeds do we expect in this interval? How many weeds do we expect in this interval? Okay, and that's our average. So our mu stands for average. And if you think about it, we found that we had about 2.5 weeds every square foot. So if we're doing 10 square feet, that's going to be that 2.5 times our 10, which gave us that 25. Or if you use our symbol, it's lambda times t. So the mean of these distributions is found by simply taking our lambda times t. We can get the standard deviation as well. I'm just going to give you that formula, which is our sigma. And the square, that again has a square root involved. It does turn out that it's simply just the square root of lambda t. So in this case, I'd take the square root of 25, which I know is 5, and that would have been my standard deviation. We'll also notice that we can rewrite our formula. So I'm going to go back up to our formula. We have these lambda t's in there. Well, lambda t is our mean. So we could rewrite our formula as mu to the x, e to the negative mu, all over t. Oops, all over x factorial. Sorry about that. It'll kind of work that way. So some textbooks, you'll see it working this way. Some you will see with that lambda, but they are connected just to make sure this mu is your average number in whatever region we're looking at. And we get this. Okay, so let's go to some technology and see if we can verify that 0.079 and make sure that I didn't have fat fingers and punch some wrong buttons. So first thing I'm going to do is I am going to go into StatCrunch, which is where some of you guys are working. And so StatCrunch. and show you how to do this one in StatCrunch. So again, we're looking for that 0.079 on and on and on. Okay, so I'm in StatCrunch, and similar to our binomial, the Poisson is under our calculator. So stat calculators, and you can go right down to this Poisson. Okay, so I'm going to bring this up into the center a little bit better. And my pop-up screen's got to love it. All right, so the mean, now that was that mu that we found. So that was our 25, because we were finding 25 weeds in my 10 square foot garden. And the question I'm looking for is, what is the probability that X is equal to? Okay, so now remember here, you could have any of the 4, 5 different inequalities. So you could have the 4 inequalities or the equal. You can change this number here too, because we're going to change this to a 25. Just kind of work that these were the same number. Does not always happen that way. And we're going to compute. You'll notice there's the red line. The height of that line is what it's calculating. You'll also notice this is nice and symmetric. Looks pretty bell-shaped to me. And there's our 0.0752295. And we had a few more decimals. Our next decimal was a 1. So we did the problem correctly. Yay, us. Okay, I'm also going to show you how to do it in Excel, because sometimes you will not have StatCrunch available to you, but you may have something similar to Excel, either Excel or possibly like Google Sheets or Google Charts or Google something, but very similar to Excel. Get rid of that. And again, you're just going to pick an empty cell. We're going to use this function key. Again, we're going to want to go into our statistical grouping. It's listed under some of the other categories too, and I'm doing statistical stuff. I like to look in the statistical section. I'm going to scroll down to my P's. It does go alphabetical. And there's my Poisson distribution, P-O-I-S-S-O-N, Poisson distribution. I'm going to click OK. The X, that's the X that we were looking for. How many are we looking for? Again, it's asking for our mean, which for our example was 25 as well, that lambda times T. And here, whether or not you want to accumulate things. Again, accumulating means we're going to start at 0 up to that point. So if you're ever doing a greater than, you're going to want to do a 1 minus. So here we're going to type in the word, whoops, no, we're not. We're going to type in the word false because it is not cumulative. We just want that single value. And once again, we get that 0.079522951, which is exactly what I had when I did the calculator. So we can use Excel, we can use StatCrunch. There are other statistical software out there as well, which are probably very similar to these. Just kind of have to learn what pieces go where. So I'm going to stop sharing. Hope that this example helped a little bit, and see you guys all in the next video.